In this video, we're going to start trying to compute some limits, mainly using the graph. So, just to remind ourselves, a limit is a tool that we use to describe the behavior of a function. Okay, so when we say behavior of the function, what we really are meaning here is the y values. Okay, so we want to know what are the y values doing as the x values approach some number. Okay, so our limits are normally in terms of x, and we want to know what's the y doing. Now, I'm just going to make a brief comment here. There's a very formal definition for the limit. We're not going to use that in our class, so I'm not going to go into it, but there is a section in the textbook that talks about it. Instead, we're going to we're going to define it intuitively and trying to use our intuition instead of the formal limit. So, first of all, some notation. So when we're talking about the y value that the function approaches, as some x value approaches a, what we write is lim. Okay, so that's short for limit, and underneath I'm going to write x arrow a. Okay, so this is the limit, and then in our limit we're going to have f of x, so some function. So it's the limit of f of x as x approaches a. Okay, so this little shorthand is basically saying this exact sentence in red that I wrote. Okay, so f of x is our function. Okay, when you see x arrow a, what we mean is x approaches a, the number a. And what we want is we're going to say this equals the y value approached by f of x as x approaches a. Okay, now I'm just going to write in brackets if it exists. So sometimes it will turn out that there won't be one. So the limit doesn't always exist, but we're going to talk about that in the next video. So so this limit that I wrote here, we assume is two-sided. Okay, so what that means is that x is approaching a from both sides. So you could approach a from numbers that are less than a, and you could also approach a from numbers that are bigger than a. So sometimes we want to make this distinction, and we only want to approach from one side. Okay, so maybe from the left or from the right. So we have special notation to indicate that we're doing that. So the phrase, as x approaches a from the left, so this is just the x part, we're going to write x arrow a, and then from the left we're going to put a little minus sign in the exponent. Okay, so this minus sign you read as from the left. Okay, this also means that the numbers are smaller than a. Okay, so we're approaching a from numbers that are smaller than a. Now, if we wanted x approaches a from the right, we're just going to add a little plus sign. Okay, so this is going to be x arrow a, but from the plus side. Okay, so that's from the right. Okay, which means that you're bigger than a. Okay, still close to a, but bigger. So when we're talking about the limit, we just use these under the lim notation. Okay, so the limit from the left is going to be lim, but now we write x approaches a from the left with a negative sign of f of x. Okay, if we want from the right, same idea, but I write lim x goes to a with a plus sign of f of x, so that I know I'm talking about from the right. So if you don't see the plus or minus sign like that, then you should assume that it's a two-sided limit. So you have to approach from both sides. So I'm going to make this definition a little bit more formal, okay, but like I said, not as formal as we could be. And I'm going to define what it means for x what it means for the limit to exist as x approaches a. So if f is a function and a and l are real numbers, so if two things happen, okay, so 1 and 2, if both these things happen, then L is the limit as x approaches a, and we would write lim as x goes to a of f of x equals the number L. Okay, so what we need to happen is as x takes values closer and closer to a, but not actually equal to a. Okay, so we never actually care what happens at a, only near to a. Okay, so closer and closer to a, but not exactly a. And because we're going to be talking about a two-sided limit here, it's going to be on both sides. Okay, when you're talking about the one-sided limit, you're just going to change this. Okay, so on both sides of a, the corresponding values, of f of x, or the y values, should get closer and closer to L. Okay, so the thing that we think the limit should be. So that's one thing. We also should be able to get as close as we want to L. Okay, so that the value of f of x can be made as close to L as desired by taking values of x closer to a. Okay, so the reason why mathematicians don't really like this definition are these type of weird words here. So closer and closer happens a couple of times, and also as close to L as desired is another. These aren't really well defined, okay, but you can imagine what's happening here. So number 1 says that as we get close to A, the y values get close to L. Okay, that's what number 1 says. Number 2 says that we can get as close to L as we want by taking values closer to A. So the closer to A that we get, the closer to L that we get. Okay, so it gets infinitely close to the number L. Okay, that's when we would say the limit is L. Okay, so that's sort of the intuitive definition. So just to remind us again, when we see this notation, so limit x goes to a of f of x, notice that there's no plus or minus here. This represents a two-sided limit. Okay, so what that means is we approach a from the left and from the right. And we want the y values to approach the same number. Because we couldn't say that the two-sided limit was equal to two different numbers. Okay, so we want it to be the same number so that we can say the two-sided limit exists. So with that in mind, I think it's hopefully clear that this fact should be true. So the two-sided limit, as I approach a of f of x, exists if and only if the one-sided limits, so the limit as x goes to a from the left of f of x exists and is a number, let's call it L, and the limit from the right exists and is also the same number. Okay, so we need the left limit and the right limit to be equal, and they're both equal to some number L. Okay, so this is kind of useful, usually if you want to show non-existence. Okay, so particularly useful to show non-existence, but can also be useful to find limits as well for particular functions, okay, that we'll see later. So let's do an example. So here I have the function f of x is x minus 2 over x squared minus 4. So let's think about what this function looks like. I'm going to write it down here. So we want to compute two limits. The limit as x goes to 0 of this function, and the limit as x goes to 2 of this function. Now, x equals 0 is in the domain for the function, whereas x equals 2 is not. So f of x actually has no point at x equals 2, because if I try to plug in 2, I'm going to get 0 in the denominator. Okay, so that's a bad thing. Now, f of x, we could factor the bottom because it's a difference of squares. Okay, so the bottom factors as x minus 2, x plus 2. And now, as long as x is not 2, we can cancel these things and get 1 over x plus 2. Okay, so this is f of x as long as x does not equal 2, because you can't cancel 0 over 0. Okay, that's not equal to 1. But in every other time, we can cancel. Now, I'm going to draw you a quick picture for this one. So we talked about rational functions before. This one's going to have a vertical asymptote when x equals negative 2. And it's going to look like the x squared, the 1 over x graph, but it's been shifted 2 units to the left. Okay, so we get something like this. And then over here, it's going to be something like this. Now I need to be careful because when x is 2, I have a hole because x equals 2 is not in the domain. Okay, but the graph is going to look something like this. So what we want to think is what happens as x gets close to first 0. Okay, so now 0 here is a nice point. Okay, the graph is smooth around there. And in fact, we could find this point. Okay, so when x is 0, the y values are going to be negative 2 over negative 4, which is positive 1/2. Okay, so that would be the coordinates for that point. So now if we think as x gets close to 0, so we're approaching from this side, from the left and from the right, we're going to follow the curve. Okay, and on either side, we're getting close to this y value here, where the point is, so 1/2. So it turns out that this first limit is actually just 1/2. Okay, which happens to be the point at 0. Okay, so at f of 0. Now, if we try to do f of 2, like I said before, we're going to get 0 on the denominator, but we're also going to get 0 in the numerator. Okay, so what we get is 0 over 0. What this means, so this is bad. Okay, we don't know what that is, but it usually means some more work required. Okay, so we need to do something here to try and figure out what the y values approach as we get close to 2. Now, because I've drawn the graph for you, we can actually use the graph to figure this out, which is what we're going to do in this sort of section. So think about as we get close to 2. So I've changed colors to green here. So when we get close to 2 from the left, I'm following the curve this way. Okay, and as I get close to 2 on the other side, so from the right, I'm following the curve this way, and it looks like we're approaching this hole. Okay, so wherever that y value is, okay, that's going to be the y value that these approach. Okay, so we want the coordinates of that hole. So think about what's happening. remember that we have this simplified version of the function. The simplified version of the function. So as long as x is not 2, we can use the simplified version. Okay, so that means if I'm 2.01, I can use the simplified version. If I'm 2.0001, I can still use the simplified version because I'm not equal to 2. So this y value that we're missing here is going to be the y value that is approached by this function. Okay, so that's what we're going to use to find the coordinates here. So we know the x value is 2, the y value is going to be 1 over 4. Okay, so this is, you plug in x equals 2 into 1 over x plus 2. Okay, so that's 1 over 2 plus 2. So that's how we find that. So this limit, the second one, as we get close to 2, is actually going to be 1 over 4 is what we're getting close to. Okay, and it turns out that one thing we can always do, and so we should try first because it's the easiest thing to do, when we're trying to calculate a limit, we should try to plug in the number. The number that x approaches. Because if this is a nice number, like it was for 0, and we just got 1 over 2, it means that the graph at that point is nice. So you're going to approach where the point should be. Okay, so I'm going to write here, if nothing bad happens, then you have your limit. Okay, so what I mean by bad is you get a divide by 0, you get 0 over 0, which is also bad. You get maybe a negative under a square root, or a negative within a log, or something like this. Or you have a piecewise function, which is what we're going to see next, and it splits at that point that you're trying to plug in. Okay, that would be also bad. So then we can't use that method. But often it will work out and you'll get a nice number. Okay, so then you're done. That's all you have to do. So let's try another example. So here we only want one limit. Okay, the limit as x goes to -2 of f of x. Okay, but we have this complicated function for f of x. So hopefully you know that this is a piecewise defined function. Okay, so it tells you when to use which part. Okay, so these things over here are telling you in which category to use which equation. So if you're less than -2, you're going to use this equation here. If you're equal to -2, you're going to get 1 for your answer. And if you are bigger than -2, you use this other equation. Okay, so that's how you use a piecewise function. So if we wanted f of -2, okay, -2 is in this middle interval. Okay, so we would know that the value is 1. But if we wanted, say, f of -1, we'd have to know, okay, -1 is bigger than -2, so we're in this third category. So I want to use this equation, so I'd have to do -1 squared minus 7, and I would get -6. Okay, and if I plugged in something less than -2, I'd have to use the top one. So because we want our limit at -2, and -2 is where this function splits, different things could happen as we approach -2. So what we're going to want to do here is use the left and right limits. So suppose we take the limit as x gets close to -2, we're going to do from the left first of f of x. Okay, so that's why I have the minus sign and the exponent there. Okay, so if I'm using from the left, this means, remember, that we're smaller than -2. Okay, that's going to put us in this first interval. So when we're computing this limit, I don't need to use f of x anymore because I know I'm going to be in this 2x plus 1 part. Okay, so I only use this, I'm going to have to use this equation for sure because we're looking at numbers that are slightly smaller than -2. Okay, now, once we're trying to do the limit, we can plug in the number. If it works, then we're happy. So this is going to be 2 times -2 plus 1. So I'm going to get -4 plus 1, so -3. I got a nice number, so this is my limit. Okay, now what I want to do is do from the right. So I'm going to do all of that again, except from the right this time, which means that we're slightly bigger than -2. So that means we're going to fall into this third category here. So I need to use the equation x squared minus 7. So remember, try and plug in the number. Nothing bad's going to happen here. So I'm going to get the answer to my limit. So -2 squared is +4, minus 7, I get -3 for this one. Now notice that these two limits are the same. Okay, now they're both not equal to the actual value at -2, okay, but that doesn't matter. Because remember, when we're thinking about limits, we don't care what happens at the point, but only what happens near the point. Okay, and near the point, the y values are approaching -3. So here we would say the two-sided limit, so the limit as x goes to -2 of f of x equals -3, because the left and right limits both equal -3. Now I want to show you what this looks like in the graph, so hopefully you're a bit more comfortable with it. Okay, so at -2, we have a point at 1. Okay, when I'm bigger than -2, I have to follow, maybe I should just write my function here so that we have it. So it's 2x plus 1 when x is less than -2, 1 when x equals -2, and x squared minus 7 when we're bigger than -2. Okay, so when I'm bigger than -2, I follow this parabola, which has been shifted down by 7. 1, 2, 3, 4, 5, 6, 7. So I'm going to get a point here, over 1, up 1, over 2, up 4. Okay, now this is where x equals 2 though, so we're actually going to have a hole there. Okay, so I get this parabola shape on this side. Okay, something like that. And then when I'm less than -2, I have to follow the line 2x plus 1, which if you want, you can, it's a line in slope-intercept form, so it's useful to graph if you start at the y-intercept, and then the slope is 2, so I want to go to the left, so I'm going to go down 2 over 1, down 2 over 1, and I see that, oh, I meet that hole. Okay, down 2 over 1, down 2 over 1. So now I know where the line goes, but I only want the piece of it that goes when you're less than 2. So those other red dots I can just ignore, okay? Or I can erase it actually here. Okay, so this is what our function looks like. So notice, as we get close to -2, okay, from the right, we're following the parabola. The y values are getting close to this -3 value. And as we approach from the left, we're following this line. Okay, so we're also approaching the y value -3. And this point here means nothing for the limit. Okay, we don't care that that point is there. Okay, so that's what that's what a piecewise function looks like. And often when you're computing a limit, when your limit is where your function changes, it's useful to use the left and right limits. Okay, so that's a brief introduction and reading from a graph when the limits exist.